So I want to go over a problem that does show up in the homework, and it's something that's not covered in the section. It's something like this. Now, with this, we're going to do the same procedure. Where things get different is when we start talking about the horizontal or oblique asymptotes. We're going to get a situation where P of x is 2 more than Q of x, and that's not one of the options they discuss in the section. So let's go through this one. So y-intercept. Again, with this, we're going to let x equals 0 and find y. So we get this. Zero to the fourth over 0 squared plus 1. And this will just be 0 over 1 is 0. So what this says is that the x-intercept for the y-intercept, when x is 0, y is 0. So we're going to get this. And there we are. X-intercept. Same idea, just things switched around. We're going to let y equal 0. We find x. So in other words, and again, you can multiply both sides by x squared plus 1 and x squared plus 1. And so what you're going to get, something like this. Divide both sides by 2. Take the fourth root. We're going to get x is 0. So this means, again, and this is the same point that we had before, we get 0 and 0. When y was 0, x came out to be 0. So it's just that point again. All right. Now for vertical asymptotes, again, we're going to set vertical asymptotes or holes. We're going to set Q of x equal to 0. And solve for x. And what we're going to get right away is, well, we're taking the square root of a negative number. And for us, that's not something we're going to allow because we're only working with real numbers instead of complex or imaginary numbers, at least for graphing these functions. So this means no vertical asymptote, no holes. Now where this gets tricky is the horizontal asymptote and the oblique asymptotes. And what we're going to discover is we have neither. The reason is the degree of P of x, in this case, is equal to the degree of Q of x plus 2. Or we have 4 equals 2 plus 2. And we're not given any guidelines for this. So what we're going to do is we're going to treat this again like end of behavior. And the idea is that, well, we're going to divide these. And when we divide these, we want to look at what comes out if we ignore the remainder. Because again, what we're going for here is how does this function behave as we get farther away from 0. So let's try that. Let's perform the division and see what function pops out. So we got to do long division with this one. All right. So our first cycle of division, take this, divide it into that. Again, lead term divided by lead term. So we get 2x to the 4th over x squared, and that'll come out to 2x squared. So we put 2x squared here. And then 2x squared times the divisor. We'll get 2x to the 4th plus 0x cubed plus 2x squared. And then we subtract. I'll just double check my arithmetic there. Okay. So this will subtract itself to get nothing. Nothing minus nothing is nothing. But then 0 minus 2, we get negative 2x squared. And since we have 3 terms here, I'm going to bring down both of these. So you have 3 terms that will eventually have some effect on 3 terms showing up here. So now we start again. X squared goes into 2x squared minus 2x squared, negative 2 times. So a minus 2, and then negative 2 times this, minus 2x squared, plus 0x, because negative 2 times 0, 0, and then negative 2 times 1 is minus 2. So negative 2x squared subtract itself. Anything subtract itself is 0. 0 minus 0 is 0. But then 0 minus a negative 2, that's a double negative. So this becomes plus 2. So what we get is 2x squared, remainder 2. Oh, sorry, 2x squared minus 2. And then we have a remainder 2. Or 2x squared minus 2 plus 2 over, well, our divisor, which was x squared plus 1. So when we're talking about end behavior, this means when x gets far away from 0. That means, say if we're going down the x-axis, x becomes massively big. If you take a constant number and divide it by a bigger and bigger and bigger and bigger number, this becomes 0, practically 0. Same thing happens if you get farther from the x-axis in the negative direction. So this remainder is going to go away. So for large values of x, our function is going to eventually follow this, but for large values of x. So I'm just going to say, I'm just going to call it an asymptote of sorts. 2x squared minus 2. Now, of course, a question we want to answer, does this intersect that asymptote? And it's not going to, because if we perform this division, when we did, we got this plus a remainder. So this divided by this, which is our function, does equal this, but plus a remainder term. If we get rid of the remainder term, this will no longer equal this division. But if you wanted to go through the steps just to check it, the main idea is this. And then solve for x. we multiply both sides by x squared plus 1. So this will have to FOIL. We'll get 2x to the fourth. Let's see, minus 2x squared plus 2x squared minus 2 is equal to 2x to the fourth. Make sure I did my arithmetic right. Okay, that looks good. And we can see there's problems here. Subtract 2x to the fourth. Subtract 2x to the fourth. So you get minus 2 is equal to 0, and that's, of course, impossible. So sure enough, I mean, this will not cross over this. So how do we graph this? Well, we have no vertical asymptotes or holes. We do have an intercept, an x-intercept. And, well, now it's time for test points. Let's see what we got. Y-axis. That there. So let's choose some easy test points. Let's say we choose 1, -1. So f of -1, this will be 2, -1 to the fourth, over -1 squared plus 1. This will be 2 over 2, or 1. If we try f of 1, we're going to get the same thing. F of 1 is 2, 1 to the fourth, over 1 squared plus 1, 2 over 2 is equal to 1. Oh, I'm sorry, this is also 1. My apologies. 1 and 1, there we go. Sorry, it was 2 over 2 is 1, so f of -1 is -1 and 1. All right. Now, let's try to graph this. So we're going to need to try to graph this asymptote. And so a good way to go about it might be using, say, intercepts. So let's say we want to find x-intercepts. And this, again, is for the asymptote. So you find the x-intercept when y is 0. So 0 equals 2x squared minus 2. Or you can factor out a 2. Divide both sides by 2. And this is the difference of squares. So we could write this in terms of factoring, or we could do it another way. We could add 1 to both sides, square root it, plus or minus 1 is x. But again, what you could have done here, difference of squares. That becomes that. So this says this will be 0 when x is -1. That will be 0 when x is 1. So you're going to get the same result. So all right. So that gives us some x-intercepts. So I'm just going to record those here. We have -1, 0, 1, 0. And we can look for this is really a parabola, so a vertex would be really helpful. And for this one, the vertex is going to be the y-axis, so a y-intercept would pretty much give it to us, but we could do the vertex formula as well. So here we have A is 2, B is 0, and C is -2. So we need negative B or 2A. That's our x value. So -0 over 2 times 2. Well, that's just going to be 0. And then we plug this back into our formula. That'll give us y. So we get 2 times 0 squared minus 2, which is 0 minus 2, or -2. So for this, we get a vertex 0, -2. So now let's try to graph it. So there are no vertical asymptotes. We do have this asymptote that does something like this. We have a vertex here, and it passes through the x-axis at -1, -1. I'm sorry, negative, that's +1. Ooh, there we go. This is -1, and that's +1. Now our actual function, though, the y and the x-intercept turned out to be the same point. So 0, 0. And doing our analysis, we figured that this is never going to cross this asymptote. So really the only place it can go is like this. And we do have some test points here. So it'll come through here. And through here. I want to forget those test points. So we have 1, 1 for a test point. So we'll go through here. There it is, 1 and 1. And then we'll go through here and make sure we stay on the inside of this asymptotic area, or the asymptotic curve. And that's it. If you have any questions, let me know.